trends. Yeah, Sven is going to talk about fast and non-invasive assessment of aggregation trends in broad-chain solutions.
Well, thank you very much, Yuri, for the kind introduction. It's a great pleasure for me to present to you some work that was actually done, all the practical parts of it, by Jonathan Rubin, who will later in this session talk about other work he did. But I guess since I've had a little bit of input in the conceptual part of this, I have the honor of presenting this. So fast and non-invasive assessment of aggregation trends in protein solutions, and obviously I don't have to say anything anymore about the problems associated with aggregation in the cases that Yuri discussed in some detail. But I'd like to point out that protein aggregation is a problem as well when we think about therapeutic proteins, because aggregation there can reduce the efficacy of the therapeutic and in some cases even cause toxicity. Very often the difference between a non-aggregating and an aggregating solution of therapeutic proteins can be exposing the protein to some buffer medium that we'd like to store it in. And that in itself can sometimes cause aggregation. And it's a problem. It's even a problem to describe aggregation. Especially the long-term stability against aggregation is hard both to monitor and still impossible to predict in general. So it would be awfully nice, especially for the formulation of new therapeutic proteins, if we had something like a fast and inexpensive way of determining mid- and long-term stability in different storage media. And by inexpensive, I mean convenient, both in the sense that it wouldn't take expensive equipment that's not readily available in most labs, but it would also mean a way to assess stability that doesn't use up a lot of sample, which is often expensive. And any test that actually leads to the aggregation of protein will typically be problematic in that sense. Now, the inspiration for our approach to this actually does not even come from the world of proteins. Oh, sorry. Let me go back and qualify also what I mean by different storage media. Here our emphasis will be on the effect of different ions that we have in these storage media. And the effect of ions on proteins is something that's been investigated by Franz Hofmeister already in the 19th century, who found that hen-egg white lysozyme had a very different tendency to denature depending on what types of ions it was exposed to. And so he ordered, in this case, anions in a series according to their tendency of denaturing or stabilizing the protein. And largely for historic reasons, we call the more denaturing ones chaotropes, because originally it was thought that these ions cause chaos in the structure of water, that they are incompatible with the natural order of waters, and the more stabilizing ones are often referred to as cosmotropes, or order makers, because it was originally thought that these are more compatible with the order of water. But that's a bit of an outdated way of looking at things. We don't think that water structure is the main distinction, but there are a lot of other physical-chemical differences between ions, and if we look at a number of different physicochemical parameters, what we find is that we always retrieve the same sort of ordering among these anions, where chaotropes tend to absorb to interfaces, whereas cosmotropes tend to be depleted from interfaces and rather accumulate in the bulk liquid. Because of that, chaotropes will tend to decrease interfacial tension, whereas cosmotropes increase interfacial tension. There's an opposite effect on the viscosity of the medium, which is also used to quantify chaotropicity or cosmotropicity. And so we expect that this has to have a big impact on protein aggregation in general as well. And of course, protein aggregation is often linked, as we've already heard, to unfolding, in some cases misfolding in ways that are not generally easy to understand. Yet, we were inspired by a description of aggregation in much, much simpler systems, which is systems of simple spherical particles, so-called colloidal particles, floating around in liquids, which just through electrostatic and van der Waals interaction can also come together, form aggregates, dimers, and higher order aggregates. And by looking at the way that we usually describe that type of aggregation, we came up with a way of addressing protein aggregation. And if we look at the way that the onset of aggregation, that is the formation of dimers, is typically described for these particles, we have this idea that the dimer formation, which is sort of the initial onset of aggregation when things start to go wrong, the speed of that can be described by a second order rate constant, which depends crucially on the pair interaction between the two particles, and also on their hydrodynamic interaction in ways that are reasonably well understood. And so this is what happens when particles aggregate. On the other hand, under conditions where they don't aggregate, for instance in media of much less salt, you can still get some signature of the interaction between particles, even without any aggregation going on. And that's by looking at the diffusivity, the diffusion coefficient of particles as a function of their concentration. There is a type of virial expansion for the diffusivity, and this linear coefficient in this expansion gives us a first order idea of what the interaction between particles does. And conveniently, it also has in it a term that's sort of the signature of the thermodynamic interaction, the pair interaction. This is the familiar osmotic virial coefficient, often considered in protein studies. But crucially, there's also a term that describes the hydrodynamic interaction, closely related to this term here, and which is a frictional virial coefficient. And so, looking at this, we said, well, could we carry out some diffusivity measurements here? This is something one can do easily with standard dynamic light scattering, and determine these interaction parameters. Yeah? We'll call this diffusive virial coefficient the interaction parameters, and predict from that what would happen if we cranked up this interaction by exposing the system to a lot more of the same types of ions. Would that be an option? And so the first types of proteins that we looked at were ones that somewhat resemble spherical particles. These were globular proteins, BSA and lysozyme, apart from both being globular and model proteins. There's quite a few differences between them as well. I won't go into here. Instead, what I'll show you is the result of some measurements in the stable dispersion or stable solution of lysozyme in the presence of different amounts of sodium salt where the N ions range here from sulfate to iodide. And what we see is the diffusivity as a function of protein concentration normalized by the dilute limit. And so the slope of this you can read as the interaction parameter. And what we find is a trend where, you know, all of these slopes are positive in the case of lysozyme, but the more chaotropic the ion is that the protein sees, the smaller this slope becomes. Smaller this slope becomes. On the other hand, for BSA, we see there's, in the case of sulfate here, we get a positive slope. All the other ions have negative slopes. There's still sort of a trend that the slope becomes smaller or more negative with increasing chaotropicity, but it looks quite different from what we had for lysozyme. Now, what we did was we exposed these systems to a lot more of the same types of ions and actually measured coagulation rate constants. These are accessible through the change in hydrodynamic size, also something one can obtain through a dynamic light scattering. And we plot them here in a logarithmic plot, the rate constant, so the larger this number, the faster aggregation proceeds as a function of the ionic strength of these salts. And again, we see there is a trend that with increasing chaotropicity, it takes less and less of the salt to reach a certain speed of aggregation. That's the way to read this. This is for lysozyme. This is what it looks like for BSA. And normally, in comparing aggregation kinetics, what you would like to do maybe is to say, okay, what's the rate constant for one protein? What is it, or in one medium, what is it in another? But we see that that would be difficult here because aggregation proceeds in very different ionic strength regimes. So what we proposed doing was to say, okay, let's take as a measure of stability against aggregation the ionic strength of the medium that we're investigating that leads us to some randomly picked threshold aggregation rate constant. Now, if we need a lot of salt to reach this threshold, then it's a more stable system. If we need little salt, it's destabilized easily, so less stable. And here is a comparison of the interaction parameter measured in non-aggregating systems and this measure of stability, the amount of the ionic strength in that medium required to induce a threshold aggregation. And as you see, there's a very nice correlation both for lysozyme and for BSA, even though the absolute values, for instance, for this interaction parameter vary widely between these two different proteins. What that tells us is that any differences in their aggregation behavior is actually fully captured already by the change in diffusivity with protein concentration in a stable system. And so we would be able to predict relative differences by just looking at stable solutions with a method, dynamic light scattering, that will give us these interaction parameters within minutes and without using up any of the sample. Of course, we're interested not in just model proteins, but also in less globular proteins. And so we looked at a humanized IgG1, both with and without glycosylation, that was provided to us by collaborators at Bioengineering. And we found that, again, in the case of, well, here are some data on the coagulation rate constants plotted for as a function of ionic strength for both the glycosylated protein, that's the solid markers, and for their aglycosylated counterparts, that's the open markers. And this is what we find in the chaotropic range. For the cosmotropes, we find a completely different behavior where even at relatively high ionic strength, we typically see aggregation too slow to even quantify in this way. Yeah? In some cases, as for formate and acetate, increasing the ionic strength more makes aggregation come to a screeching halt. So quite a different scenario here, but at least for the cosmotropes, we can basically play the same game that we did before for the model proteins and correlate the threshold ionic strengths, which we read as stability against aggregation, against the measured interaction parameters, and find reasonably good correlation again between those two. Although our interaction parameter seems to distinguish very clearly between the aglycosylated and glycosylated protein, and is more sensitive to that than the aggregation data themselves. The reason we believe that that is true is because the pair interaction potential, which we expect to have a general shape like this, where you have a primary minimum, an interaction barrier that you have to overcome in order to achieve aggregation, will generally be lowered if we add more salt to the system, screening all electrostatic interactions. That would lower both the primary minimum and the interaction barrier, but glycosylation, in all likelihood, being a very short-range effect because of the steric hindrance it provides, would essentially affect only this primary minimum, not so much the interaction barrier, and it is the primary minimum that our interaction parameter is most sensitive to, whereas the aggregation rate is most sensitive to the height of the barrier. So this can be understood. This is what it looks like if we plot all the interaction parameters. We see a clear dependence on the cosmotropicity or chaotropicity as expressed in the so-called Jones-Dole coefficient. Here are the names of the ions corresponding to this, and we see a clear trend here in the chaotropes of basically lowering the interaction parameter, and as we saw here, also lowering stability at the same time. Okay, with that, I'd like to summarize that basically we have a non-invasive and very fast way to assess qualitatively differences in protein stability in different media of different ionic composition, using just standard DLS equipment that is excellent for globular proteins and seems to work quite well for chaotropic salts, still serves as a telling heuristic for the effect of cosmotropes, and is very sensitive, as I showed you, to glycosylation of antibodies. And with that, I'd like to thank our partners at Biosharing, the Behrens and Behrens groups, and our funding agencies, in particular the Center for Pharmaceutical Development.
We have time for one important question. As I said, Mark was first.
So which is going to provide greater stability? That is an optimally selected salt or DI water?
An optimally selected salt.
So what about when there's zero salt? You didn't have
Oh,
that. I mean, as you went to lower and lower ionic strength, things got better.
Well,
So in the limit, you're DI water.
well, actually, I didn't show any data for DI water, right? In the case of, let me maybe go back. Yeah? Here in the case of antibodies, and cosmotropic salts, we do find that in many cases the most stable scenario occurs at elevated salt concentrations. Really, what this method is good for is not to tell us at what specific salt concentration of a given salt we should operate. But if we have knowledge of stability in one medium, how a different medium would compare to that. So it's relative differences. It turns out that the differences in the interaction parameter that we see when no aggregation is visible at all, and the trend in the speed of aggregation that we see when aggregation is so fast that we can easily follow it, are the same. We get the same order, which is nice because we can then hope that for an intermediate rate of aggregation, something that happens over weeks or months, will still have the same order, because we see it in the slower and in the faster case. And it's, of course, neither the case of a completely stable system, nor the case of one that aggregates fast and invisibly in front of our eyes that we're ultimately interested in, but the intermediate slow aggregation.
Okay, so I think for those who don't have time,